My name is Judy.
My name's Juliana, and today we're here with a special guest.
Michael Heafy.
So what area of study are you in, and what degree do you have?
So I'm in earth science. I graduated with a geology degree.
Okay. So where did you go to school?
I went to Southern Connecticut State University.
Okay, and what are you doing now for a living?
Now I'm an industrial hygienist at a local company.
Okay.
So we have a couple questions. The first being, what is the concept of plate tectonics? And if you could just explain a little bit about it.
So the concept of plate tectonics was actually originated, was an original idea of Alfred Wegener. And basically, it was the idea that the plates which make up the Earth's crust are constantly moving. So you have two different types of plates, oceanic and continental, and basically they are constantly moving around one another.
Okay. So could you describe the different types of plates? What makes them different?
So oceanic plates are very dense, made almost entirely of basalt. They're very mafic and ultramafic rocks. And because they're so dense, that's why they are lower towards the Earth's core and have the oceans on top of them. Whereas the continental crust is comprised mostly of granitoid cores, which, for example, if you looked at the United States, most of that granite core is actually in eastern United States and Canada, and all of the other material is actually just other less dense material that's been accreted on, but it's really those granite cores that make up each continental plate.
And how does plate tectonics theory relate to the creation of volcanoes?
So, actually, I'm going to backtrack a little bit here, but another important thing for the plate tectonic theory is also the Wilson cycle, which is basically the description of how oceans are kind of created and destroyed, where you'll have rifting centers form on continents. When those form, or I guess they could form in oceans as well, but when those form, you have uplift in the area. An example of that happening today would actually be the East African Rift Valley. And as it continues to spread, you'll eventually sink below sea level because it's such a dense material. And when that happens, you obviously have water then over it, and you're starting to spread out wider and wider. And when the ocean will continue to keep getting bigger, such as go from what the Red Sea is today to something like what the Atlantic is, and eventually that process is reversed, where instead of continuing to grow, eventually subduction will start to occur along the edge of the oceanic plate boundary. And when that occurs, the ocean is going to start closing up, because somewhere else there's going to be another mid-ocean ridge that's spreading, and if it's spreading at a faster rate than the rate of the pre-existing ocean ridge, then the subduction is going to be occurring and closing off that ocean. It continues to get smaller and smaller, kind of like the Mediterranean today, which is a sea that's being closed off. And eventually it will completely close off, and you'll end up with continent-to-continent collision where mountains are built up. Now, that continent continent-to-continent collision where the mountains are built up is not where you'll see volcanoes. Where you will see those volcanoes is where the subduction is occurring. So basically, when you have that oceanic crust sinking down back into the mantle, basically when it's going down, it's carrying with it a lot of ocean water. So as that water is brought deeper into the mantle, it becomes under a lot greater pressure and a lot higher temperatures. So what that leads to is the water is actually forced out of the oceanic crust as it's dragged down, and the heated water starts to actually melt the surrounding mantle rock that's around it. So as that happens, the mantle melts, and as it does that, it rises up, and that's where you start to see magma plumes and rising up to the surface, where you'll start to get volcanoes forming along those plate boundaries.
Okay, so that's really interesting. I didn't know that water could do that, and that made the lava. So how about earthquakes then? Because I'm sure plate tectonics, since everything's moving underneath the earth, it probably has to be responsible for a lot of our natural disasters.
So yeah, basically the Earth's crust is constantly in motion, even though you don't necessarily feel it. And a lot of the major earthquakes happen along those plate boundaries, because that is where most of the motion is happening. Although it is not uncommon for the earthquakes to happen outside of that area. For example, just today, there was an earthquake in New Jersey. I think it was 1.8 magnitude. So it wasn't a major earthquake, but there are no plate boundaries near New Jersey. So there is still faulting and whatnot that occur in the areas away from plate boundaries that can cause earthquakes. But in terms of the plate tectonics causing earthquakes, those are obviously on a lot larger scale, which is why they have such a higher magnitude. So just for example, I'm blanking on the name of the trench. Well, the trench off the coast of Japan, obviously that's an area where you're having the subduction occur, and you have volcanoes forming all along that island arc, which, like, Mount Fuji is one example of one of those volcanoes. And so basically, rock is very brittle on the surface. So as you have all these forces working against one another, so Pacific Ocean still has a mid-ocean ridge. It's trying to expand, but there's still other forces acting on the continents, forcing them one way or another. So if the other acting force is like spreading at a faster rate and therefore with more force than what a slower Pacific mid-ocean ridge is doing, then it's kind of squeezing the areas in between, and that's actually what ends up causing the subduction of the oceanic crust at those areas. But when the oceanic plate is basically being when the oceanic plate is meeting with that continental plate, it doesn't just slide under. It's possible for that to happen occasionally, where it will just slide under and not much tension is really not tension. I guess stress is really built up in the rock, because that can happen. But most of the time, what you'll see happen is that basically the continental crust of the rock will be sticking to the oceanic crust as it's trying to move. So what happens is you'll actually see like the continental crust kind of like bending down with it, and actually causing uplift near the surface there. But eventually there's too much force on it, and it will kind of snap back out. So when that happens is you're causing an earthquake near the subduction zone, releasing basically all of that force that's been built up through the motion of plates.